we're happy to have the last lecture by Kantaro Ohmori about higher algebras in theoretical physics.
Thank you. Okay, so thanks for coming to the last one. And okay, so I was talking about in the morning. I was talking about two vector, which is nothing but the modules, and then now I'd like to talk about the two linear maps, and that's corresponds to the topological interface. And well, idea is the same. It just now we have two systems that each described by different Frobenius algebras, and then okay, then we want to consider the interface. So that's so we insert some another vector space, one vector space that I call B, and then we want to have this to be topological in the sense that we can extend our commuting projector Hamiltonian to involving B. Okay, so here we have this side we have A1 and this is A2, and we have the same kind of bulk Hamiltonian. Terms, and we want to be able to write the Hamiltonian term here, or transform matrix here. So we want to do something like this. And okay, so this is just a two-sided version of what we did. Okay, so in the morning we are talking about the boundary, just boundary, and then we said that we want this to be a consistent action of A1 to B. Now we have two sides, so it just corresponds to the A1, A2 bimodule. And the bimodule means that A1 acts from left, A2 acts from right, and the two action commits. Two actions should commute because we want this projector and that projector should commute. So okay. So this is what we can call two linear map. Now, at this stage, to organize those structures, I'd like to introduce the two category of two vector spaces. Okay. Maybe just look. So, well, category is some mathematical gadget to organize things, and that two category is just a higher version of it. So, as in the ordinary category, this two vector space contains the data called objects and one morphism and two morphism. Now, objects in this particular two category of two vector spaces, we of course the objects to be two back. Like this is two vector space, which is the Frobenius algebra. Now, one morphism, we want this to be a linear map. So for each pair of two vector spaces, we assign the bimodule or the topological interface. So this is called A2 bimodule. Okay, yeah, I re-emphasize that this is not really a map from A1 to A1 to A2. If you have algebra homomorphism from A1 to A2, then you can make it a bimodule by taking B to be A2 itself, and A1 action is via that homomorphism. But in general, this is a more general version of map, and that's what happens typically in this kind of higher category business. Okay, so now this is bimodule, and then okay, so this is in particular vector space, and if you have two vector spaces, you want to consolidate this. So that is why you have the third layer. So if you have two one-morphisms, B1, B2, that sharing the same source and target, then, okay, so this contains a bimodule map. Okay, so this is bimodule maps. Okay, so the bimodule map in this physical picture is that if you have two different interfaces, then you can connect the two different interfaces with a linear map. But we want this linear map commutes with the projector Hamiltonian here and there. And that's the compatibility condition we require for F. Okay, so that's
Can I ask a question?
yes.
I'm a bit confused about the full deliverability condition. Is it so all objects here are assumed to satisfy to be fully dualizable?
Oh yeah. Oh, okay. So here I'm assuming I'm really talking about the free dualizable,
Okay.
and then this is.
So this is the algebra which satisfies all those.
Yeah. I'm assuming that this to be the separable algebras.
Okay. Thanks.
Yeah. I'm assuming that this is a free dualizable. And the yes. Okay. Well, bimodule map condition is specifically it's like A1, E2. This is the for linear map F to be a bimodule map. Here's the action of A1, small A1 coming from large A1 and small A2 coming from large A2. So this is bimodule map condition. Any question? And yeah, so okay. The physics picture is this. Maybe I rewrite here that we have objects gives you a 2D topological system, and then one morphism is the interface, and then two morphism is the interface of interface. It's sometimes useful to draw a Poincare dual of this picture. So we have like this. and this is just a Poincare dual. This is one morphism. And if you have two one morphisms sharing the source and target, then you can draw two morphisms this way. So, I mean, this is just in case you encounter this kind of diagram. And then, okay, then these are morphisms. So some arrows in this drawing, and so we want to be able to compose, and we can. So the composition is that if you have two bimodules. So this is basically one morphism from A1 to A2 and A2 to A3. And then you can construct the tensor product over this part. Okay. I mean, this B12 is in particular the right module, right A2 module, and B23 is in particular a left A2 module. So you can take tensor product over A2, and you can show that this has a structure. This vector space has a structure of A1, A3 bimodule. So this is a composition of one morphism. And then, but for two morphism, it is just a so-called vertical composition is straight. That it's just this is bimodule map, and you can compose as linear maps. Okay. And
the B23, is that a one morphism?
Oh, sorry, this is one morphism. Thanks. And and there's an identity among this composition, and which is A itself. So if you have, in particular, you can pick A, maybe A1 as A1. If you have an algebra itself is a bimodule, that itself bimodule, and the action is just coming from the original multiplication. And then you can easily convince from the definition of the tensor product of algebra that A for any B12, that A tensor A B12 is B12, is also as an effect to B12 to A. Maybe A1. Oh, no, this doesn't make sense, sorry. A2 here. A2 here.
Could I ask a question?
Yes.
I'm just trying to understand this figure that you drew here. I don't understand the language very well, but so should I be thinking of one morphisms as morphisms between the objects which are A, and then two morphisms as morphisms of the morphisms of the one morphisms? Is that?
Yes.
Can I ask a follow-up question?
Sure.
So in this diagram, why is F a point there? Are we also splitting horizontally?
Oh yeah, you can do that. Yes. Here. So in this setup, everything is topological, so you can kind of do it whatever. Yes.
So then the lower half you're calling B1, and the other half you're calling B2?
Yeah. I should written yes. B1 and B2. Thanks. then I should flip this. Okay. The another important class of one morphisms in this two category is the invertible morphisms. So invertible morphism. Okay, and or invertible bimodules. Okay, so the B12 is a bimodule. Let's say B12 is a bimodule between A1 and A2. And then, so is invertible. It's called invertible if, as a definition, that there is opposite way. The 2-1, it's A2, A1 bimodule, such that the composition is the identity. So we can compose in this way, and this is A1, and C21 and tensor product over A1 and B12, and this is it. Recall that the A1 and A2 are the identity morphisms. So yeah, this is the two category version of saying that the FG equals to ID and GF equals to ID. So yeah, in the usual case that some map being invertible means that you have inverse. You often call it the inverse, and compose in one way and the other way, and the other way you get the identity. And this is just a generalization of that. Now, if two things are connected by the identity one morphism, then as an invertible one morphism. So then the two topological systems are actually equivalent via this interface. In other words, if you have A1 and A2, and then you have invertible interface, then you have one. So yeah, so this condition is that this is A1 and nothing, A1. And conversely, 2, A2, but then it's like what you can do is that starting from A1, here equals means that this long range physics is the same, and then and this dashed line is the identity. in the context of MPS, you have one more vertical white leg, and that doesn't matter here. So then, if you have starting from A1, and then you can divide it into three places, and then connected by the identity one morphism interface, the trivial interface, and then I use this thing to insert A2 in between, and then crush the inside using here. Then it's like A2, A2. Well, you have the other side here, but then you might push this to the other boundary. Okay. Or if it's a periodic boundary condition, then you move the other way around and crush, and then you get A2. So we conclude that if A1 and A2 have this kind of module, the inverted module, then the two systems in long range the same. Now, yeah, and there's a word for this. So,
hello, I think that the B12 and C12 in the last line was.
oh yeah, thanks. C2 here should be C21. So when A1, if there is a like invertible bimodule, A1, A2 bimodule, then it's called A1 is Morita equivalent. To A2. And the Morita equivalence is the Morita equivalence is also the equivalence of the long range physics. That's the basis here. And okay, so what is the example of Morita equivalence? Okay, so let's take A1 to be some matrix algebra, and A2 be the trivial algebra. Then E, that's the fundamental representation of this matrix, just a column vector. Then this thing acted from A1 from here, and a C. This is just a C, so you just can act from right also. And then there's also E star, that's row vectors. This is dual. And then these are the invertible bimodules. Okay, so the matrix algebra is Morita equivalent to the trivial algebra. Or in short, matrix algebra is Morita trivial. Morita trivial. In general, the A is separable algebra or semi-simple algebra. Then out in Wedderburn tells you that it's direct sum of matrix algebras, then there's a center, and the center is generated by C times in this way. Now, well, if you decompose A in as a direct sum of matrix algebras, then its center is generated by the unit matrix in one component. Okay, so that's this, and you can of course take a linear sum. Now, then if we take E to be like, so EI is a fundamental for this block, and then just sum over the simples, then this is, you can easily see that this is A, ZA bimodule the action of center commits with A action because it's center. And then, or you can also, this is basically just the direct sum of matrices. So in the same way, you see that this is invertible. Okay. So as I said that, yes.
Yes, sorry, maybe it's simple, but can you explain why it is invertible? I don't
Oh, okay. Yeah. So sorry. So yeah, that's. Well, let me explain in this case. Then this case is just direct summing. Okay, here. Well, as I said, this we are interested in matrix. We have to show this is invertible. These are invertible modules. Then we should show that this tensor product over matrix algebra is C, and then the other way around, this is matrix algebra itself. Now, this is almost definition. This thing, okay, so the definition of tensor product is like if you have B1 tensor of some M, B2 is in this tensor product is identified with B1 of M, B2. But then you can basically, yeah, you can basically using M that these two vectors are in the one directions. So you can convince that there is only one dimension remains after quotienting this for any matrix. Okay. 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 Yeah. So I was saying that A1. So A for any semi-simple algebras, A and ZA are Morita equivalent. And that's like the long-range physics are the same. So this is as a topological system with a caveat that I cannot explain, but topological system is in a sense one-to-one corresponding to commutative symmetric Frobenius. well, caveat is that we are assuming that A has a special Frobenius algebra, and that's slightly different from the known classification of TQFT. But let me not talking about that right now. You can ask later in the discussion session if you want. And the okay, so any question?
Can you show how the O times E dagger similar to equals to the
This one?
next line
This one.
how this is equals
This is matrix of n. This is a standard thing that you can, any matrix is a linear combination of, okay, so this thing is a tensor product of bra and cat. So this generated by this, right? And then linear combination of this kind of thing. This is a matrix whose ij component is 1, others are 0. And then you take a linear combination. Then you get any matrix. Yes.
So regarding this Morita equivalence, so
Yeah.
I understand it is an equivalence relation,
Yeah.
but can you comment on why it should be, I mean, it is a physical equivalence, or in other words, why physically it is not possible to distinguish A, which is a large set of matrices, from A, which is just complex numbers? Why they should be regarded as identical physical systems?
Well, one explanation is this move. A more simple answer is that I mean, basically in this dimension, the only information remains in the long range is just the number of ground states, and then like others are like washed out in the long range. So then it's very large matrix. The system coming from very large matrix is also like just one ground state. So that's the short answer. Of course, I mean, as I already said, that if you start to think about like systems parameterized over some other space or some symmetry acting on it, and then like it's this kind of Morita equivalence in that context becomes branches. So then, in that context, that even if you start from like if you forget the additional structure like symmetry, then two things are Morita equivalent. But then you start to want, like if you are thinking about the symmetry, then you want this interface to if you want the interface to respect the symmetry, then you might lose the invertible Morita equivalence in that context. So in that sense, that having the option of like going to larger algebra is going to be useful, but without additional structure in this dimension, it happens that it's just these numbers matters. I mean, this order of ZA matters. Yes. Thanks for the question.
Could you please repeat again what was the situation with pushing the outer interfaces to infinity? Like, what was the point you were trying to make?
Okay, yeah. Here, I wanted to say A1 system and A2 system are the same, or equivalent in the long range, and then that's So it's simplest that if you consider the like infinite space or just a periodic boundary condition, then here I insert two trivial interfaces. There's nothing. But then I assume that there is some two interfaces that satisfy this property. So then I split up the trivial identity, that's a trivial interface, into the pairs of invertible identity interfaces.
Yes. So, yeah. No, let's say I get up until the point you go down, but so like on the left and on the right there are still A1s.
Okay. Yeah. So then if you make the periodic, for example,
Yes.
periodic boundary condition, then you I mean by periodicity you end up with the interface here, and then you crush here. Then again this is A2 trivial interface.
Okay. This seems okay. So let's say from the point of view of periodic, I understand. Otherwise, you're saying even if it's not periodic, you can just imagine that the systems are infinitely far away from what you're studying, and you can discard them effectively. Like, I mean, I guess this is in a way the intuition of the Morita equivalence. Like the fact that we had this invertible C in the first place allowed us to write down these few steps that made us go from A1 to A2.
Yeah.
So in that sense, we should treat them as physically equivalent in this long-range topological system.
Yeah.
Okay.
Yeah. If you do have the boundaries at a finite distance, then what you can say is that still you can fuse this bimodule to this boundary. Then what you can say is that there is a correspondence between the boundary conditions between the two systems, and under that particular correspondence, the two systems are equal.
Okay, so you can say they're equivalent under this transformation of the boundary vectors of the two vectors.
Yes.
Okay, thank you.
In relation to these questions, maybe in stupid terms, so if I interpret this as are some symmetries, for example, I'm building some dualities between theories in some sense.
Yeah. So in this case, if you regard this A1 is kind of, well, in this dimension a bit too trivial, but if you go about one higher dimensions, then this A1 is your symmetry TFT. And then if you have a non-trivial like the self or, well, yeah, interesting case that if you have a self but non-trivial invertible homomorphism, then that sometimes corresponds to the Cramer-Swanny duality.
Thank you.
That's like a EM duality for the toric code. Then EMZ to symmetry for the toric code. Yeah. That's one example. Yes. Okay. So I really want to get to the 3-vec. So, but before that, any question? Okay. So then I move to 3-vec. Okay. Okay, so the 3-vec is going to correspond to the 2 plus 1 d TPFTs or topological orders. And it's a well, it turns out to have to be non-chiral topological order. I will, if possible, I will comment about that. Okay, and so let's get to this point. Okay, so well, to repeat what we did, that we consider the 2 MPS. So here, so I draw the same picture as I did. B, and maybe well, let me call this A and mu. Now, however, now I say that these are lives in the two categories of two vector spaces. Namely, A is 2-vec, B is 2-vec, mu is bimodule. Okay. So that's a way to going up the dimension. Okay. And then okay, so let me to emphasize that. Let me put 2 here. Okay. Okay. So, and I want this thing. So maybe I should tilt it over here. And I repeat my requirement in this context. So I want, for example, I want this mu 2 thing A2 is equivalent to A2, and there exists mu 2, mu superscript 2, and A2. Okay. So basically, I'm just putting spinning 2 everywhere and doing the same. Now, good. Okay, so what is this? Okay, so here, so eventually, so I skip, I do not repeat everything, and I present the final object that we get from this kind of exercise. That so we want to get the notation is awkward, but notation is awkward. Sorry, confusing. So we arrive at I'd like to call it a 2 algebra or 2 Frobenius algebra. Well, to be precise, of course, 2 symmetric special Frobenius algebra. But I don't write everything. And then so there's in particular, it is a 2 vector space. So this is underlying 2 vector space. And 2 vector space is itself a Frobenius 1 algebra. This is one algebra. Okay. So this data already includes A1. This is just underlying 2 vector space, but it's this is underlying 0 vector space. Sorry, underlying 0 algebra, which is vector space. This is vector space. And this 1 multiplication, and then I also need the co-multiplication and the Casimir element. Okay. So this is underlying 2 vector space. Then I repeat this kind of structure here. So now these are lives in, one morphisms in the 2 category of 2 vector spaces. So in particular here, it's in one form of underlying 2 vector space tensor A1. So this 2 multiplication is not really a map, but it's a bimodule from A1 to A1 to A1. This thing is also like Hom from A1 to C. It's a trivial 2-vec. And yeah, so this is basically just a module, the right module over this underlying algebra. And this guy is one tensor one. Now, I didn't close the parenthesis here, and the rule is that if you go up higher dimensions, then you need more data, or that you need to promote the constraint you impose in the lower dimensions into a data. So, for example, so I'm not finishing here. We want mu to be, so in lower dimensions, we want mu to be associative, means that mu is strictly equal to this, okay? This is usual associativity. When you go up higher dimensions, so then the intuitive understanding is that these are, each of them are two vector spaces. So this is like 1 plus 1D or 2 plus 0D, 2D system. Although I wrote just line, but there's one additional dimension. Okay. And we are weaving this 2D systems to draw a diagram. Now here, okay, then in this dimension, like what we really want is that it's hard to draw the diagram, but we don't really impose that this is exactly equal, but there is a transition from this picture to the other picture because we should imagine that there's one additional dimensions, and here is also so asymptotically this way that you have this configuration, and asymptotically backwards, then you have this configuration, then you can imagine that there is a transition. And what you demand that this transition is invertible. Okay, so here at the 2 multiplication, we demand that there is a map. This is in 2 Hom in A1, 3, and A1. Sorry, I said it wrong. No, this one. So I should say that this is mu2 tensoring over A1. So this thing is, well, this thing. Times A. Actually, I'm confused. Well, let me draw the diagram. That's easier. So, and then the two way of contracting. So this contraction again is a tensor product over A1, the underlying two-vector space. Okay, and there are two ways of contracting this bimodule. So you have two defined bimodules, and we demand that F that is also invertible. So this is also invertible. Okay, so that's this additional data. Now there are other data regarding this kind of thing, but let me omit that part. Yeah, and then so we have new data, and then we need a new constraint. So the new constraint here is a well-known pentagon identity, which is 1, 2, 3, 4. I don't think I can draw here. So you have F and you go the other way. I'll do that. Yes. And okay. So the constraint is, so sorry for being top down, but constraint is that you go from this picture. So this is tensoring 3 mu 2s, and then there are two ways of applying a composition of Fs to arrive at this configuration, and that these two maps should be equal as a linear map, as linear maps. So that's the constraint. Okay, so then I have to really be quick to try to explain examples. I explain examples, then I will also quickly give you the Hamiltonian. Okay. So examples. The first example, important example, is the two-matrix algebra, which is the underlying algebra is just B. This is B star. Yeah, B is in the objects of Tuvek. So this is just Tuvek. So V star is a V up. Then you can equip all the structures. For example, the 2 multiplication in this case, you can take it be like B tensor B tensor B. Maybe you need somewhere up. I'm not sure. Then yeah. So this is not clearly a map from A1 squared to A. This is like some gadget.
What is op? What is this superscript? What is op?
Sorry.
OP.
Op. So op is so this thing is two-vector space. So this is our algebra. Op is the multiplication is opposite way. Thanks for asking. Yes. And Okay. Another example, important example, is one commutative case. One commutative means that this underlying two-vector space, which is algebra, is commutative. This is commutative. So in other words, we can say that underlying algebra is just a bunch of C. And here A is just a label that I use to the component of C. So each CA has EA and like EA, EB. This is the multiplication of this commutative algebra. Okay. Then what happens? Then like modules are just also like bimodules participating in this kind of structure are all again bunch of C's. Okay, so in general, so this stuff should be parameterized by like A, B, C, and like C to N, A, B, C, and like EA, tensor, EB, tensor. Okay. This means that formally you think this kind of element and action of A1 tensor, these A1s, is just determined with this formula. Okay, and then it's just that any bimodules with this structure can be written in this way, with some coefficient. And then I should not be raised, sorry. Well, there's also epsilon 2. This is, I should not be raised. This is just a right module, so it's just like C to U, A, E, A. Okay, then like we want this F and if you just compute this thing, and then F is like yeah, okay, so this guy, A, B, C, X, D. So if I project for each factors that to these generators, then yeah, so it's like this bimodule looks like C and A, B, X, and D, and E, A, E, B, D, while the other contraction you can compute that in the same thing. And then, okay, so of course we have to remember the, give a basis here, and then like this factor and this factor has some inherent basis. And then F is basically map from this thing to that thing. And this is invertible linear map. Now, what is this structure? And well, if you knew to the field that this is what it is, but if you have some experience, then you should have noticed that this is actually the same data as fusion category. And if you, multi-fusion category. So this guy is going to define the tensor unit in this fusion category, and so in general it's multi-fusion category. But so that's a comment. Now, and this fact that if you just think about the two algebra with one commutative underlying 2vec, then you get the multi-fusion category is explicitly demonstrated in the Thibault de Camp paper. Sorry, the copied paper. Mess it up. Thibault paper and the what should I do? Okay, and then last third example. Let's say so this anti-strict 2 multiplication. Here, anti-strict means that so in general this is just a tensor A bimodule. But anti-strict, I mean, this is actually a map. This way, so algebra home. And then also we demand that if this two counit is also a map in this way. This is also like algebra home. Okay. Then we identify this map as a hop. Okay. Hop. And then we arrive, if you expand definitions, you arrive the hop algebra. Yeah. The antipode comes from the Casimir element. So the Casimir element is in A tensor A to A bimodule, sorry, to C bimodule. But this, it turns out in this case that this should be comes from the A to A up algebra form, which we call the inverse of antipode. And yes, so the hop algebra is another example of the algebra. Any question? The last one.
the last line? What was the last line?
Sorry, this thing. Yeah, okay, so we need a Casimir element that inverts this the by two linear maps that inverts the by two linear map coming from the composing this and that, and that's this thing. But it turns out that if you impose this case, these conditions, that this thing, this bimodule should be as a vector space, it should be A, and the A tensor A action should be like this one factor is just coming, just usually acts from this way. The other factor acts the other way with the through one algebra home from the A to its opposite. So this is, and that's, if you expand these axioms, you can, this is actually corresponds to the inverse of antipode. Okay, that.
So is the statement here that any Hopf algebra can be generated in this manner?
Sorry, any Hopf?
Any Hopf algebra?
Yeah. Conversely, if you have Hopf algebra,
if I have Hopf algebra, I can,
semi-simple Hopf algebra, finite dimensional, then it fits with the, If you impose the symmetricity for this counit, then it's a pivotal Hopf algebra. Okay. Now, okay, so let me very quickly introduce lattice model. And so to do lattice model, we need some vector space, or the Hilbert space on 2D. Okay, so how to get that? And so recall the previous part, that the two vector space that I gave you the description of 2 plus 0, 0D system, which gives you a number if you evaluate the partial function. But now we can promote that the same picture in one higher level. Then that thing gives you a vector space. Okay, so I redraw. It was just hexagonal lattice. And then here, like you put like mu and delta. I don't know, like mu and delta. Delta, mu, delta, mu, delta, like that. And those are two multiplication and two co-multiplication. What's this? Then this thing is going to give you a vector space. The explicit way of calculating the vector space, of course, these lines are like represents a tensoring over underlying the vector space. But it's also like this thing. You can also insert the complete set, if you remember. So the complete set is formed like this. This is 2. This is just 1. Okay. So then for each trivalent vertex, you like if you have mu2, then you can have like E1, E2, E3. Okay, and this is one vector space. So this thing, you put one vertex, and here you do the same for the co-multiplication. And then you have ijk, ijk. Then you take a tensor product for, so you assign this vector space, this is a vector space, with a vector space with 3 indices at each vertex. And then taking a direct product when these indices matches along the line. So that's, in a way you can locally construct the entire vector space. Okay, so this is a gives you a vector space, or if you do the C-star setup, then we get the Hilbert space. Then sorry, being top down, but I quickly give you the Hamiltonian, the projector. So now Hamiltonian is also the commuting projector Hamiltonian for each bracket. This is terrible, but the PP is a placket. Okay. And this guy is, oh yeah, so there are several ways of presenting it, but like simplest one is that we, also I didn't say, but we still demand that this 2 algebra is separable. Means that there is a bimodule map that you can do this. Okay? So this is 2 separability. So 2 separability, so just the separability is that you can just, in one algebra, you can just remove this kind of bubble. In 2 separability, you can create or remove this kind of bubble up to some bimodule map. Okay? So I put that, and then we do F move here. Then I do F move where? Here, I guess. F move here. Actually hard to do it on the fly. And then do F move here. And okay, so I don't do it anymore, but then you go back. Eventually you go back to this picture. And then lastly you shrink. Now okay, so what is this? Well, this is what it is. But if you apply this construction to the one commutative case, then you get so-called, Levin-Wen model. Okay, so recall that one commutative 2 algebra is literally just having the data of fusion category, and there's a construction by Levin and Wen, Michael Levin and Shagun Wen, based on the fusion category to create this kind of commuting project Hamiltonian, and this is exactly the same construction. Okay, if you apply like the 2 matrix algebra case, then, well, this is what it is, but the ground state is like single ground state. It looks like placket BBS, valence bond solid state. So that's like, so that's some SPT. But I think I should finish. But yeah, so I cannot tell too much. But yeah, so yes. Okay, so I stop here and take questions. Yeah.
Okay, maybe we have a time like, for a couple of questions. Otherwise, you can also ask questions in the discussion session later.
So could you say perhaps a few words about how this can be used to compute things like entanglement entropy? Because a priori, at least with matrix product states,
Yep.
The bond dimension is sort of the thing that bounds the entanglement, and for these more general things, I think Levin and Wen also had that as one of their applications.
Yeah.
So is there just a few things you could say?
I don't have very concrete thing to say, but yeah. Yeah, this kind of, yeah, sorry, yeah, I don't have anything intelligent to say right now, yeah. Let me think, but yes. Yeah, I agree that that's not really the interesting direction to think. Yes.
Other questions? Okay, well, since we are a bit short on time, let us postpone questions to the discussion session. And okay, now